All right, just testing the mic. All right, hi everyone. So we're going to talk about Kubernetes observability, specifically Kubernetes observability with Pixie and New Relic. So just as introductions, I'm Zain Asghar. I'm the general manager of Pixie and open source at New Relic. And we have two other speakers who are here in person, Natalie Serino and Omid Azizi. They're both principal software engineers on our team. So with that, let's talk a little bit about the observability landscape today. And kind of the flow is we'll talk about the observability landscape, talk a little bit about Pixie, and then we'll see some use cases and demos, and then just a little bit of a deeper dive for those who are interested in the technical details of how Pixie works. So with that, what do we see with observability today? So one of the things that I think everyone here will agree on is software is getting more decoupled, and part of this is to have more velocity, agility, and scale. Especially as teams scale out, we can build more microservices, have them be independently managed, and independently deploy. But we still waste a lot of time wrangling all this data that we need to manage, debug, and secure these applications. And part of the challenge over here is that you'll end up wasting months setting up a lot of predetermined data collection. So here's like an example of very simple HTTP service. And it's not really important to actually go into the code here, but the red part is actual instrumentation, and the green part is the business logic, right? And you're starting to see that there's a lot of work being spent on actually instrumenting code. And this is not to say that manual instrumentation isn't good or necessary. I think it actually has its use cases, and we use it all the time ourselves. But it would actually be good if you can get a lot of this information automatically without having to do a lot of work. We want easy things to be easy. One of the other challenges we see is that a lot of the telemetry data that's being captured and used is really not that useful, but you'll end up paying for it, right? I'd even say up to 98% of telemetry data is pretty useless. It's just telling you things are operating as expected. Here's the total summary of how many errors you see, et cetera. But we still end up moving all this request information to a centralized backend. And kind of this is where Pixie comes in. So we'll talk a little bit about what is Pixie and how Pixie solves some of these problems. Cool. So Pixie is an instant code-driven debugging system, which primarily focuses on the APM use case, but we also have infra-metrics, network performance monitoring, and also continuous profiling of code, which you'll see in a bit. So we're a platform that basically allows you to build observability systems. And we do a lot of this data capture internally using eBPF, which Omid will talk about later. And then we have a scripting framework on top of it to actually build all these views and also work with data that's new. And one of the other things that Pixie does is it extends the observability stack to the edge. So we install these things called Pixie Edge modules, which actually get deployed on every single node, just like you would in a traditional agent. But unlike a traditional agent, they work across all the applications that are running on that node, and they contain storage and compute co-located so that we can, with very low overhead, store, filter, and monitor the data that we're seeing. So really the three things you see is, we moved away from rigid predetermined manual collection to this code-driven instrumentation that you'll see. We moved from a cloud-only solution to something that works on the edge plus the cloud. So the nodes plus the cluster plus the cloud give you the whole visibility spectrum. So you can go from seeing high-level metrics all the way down to specific requests in the system. And those are usually stored on the edge. And then move away from all these manual and siloed interfaces to everything being API and code-driven. So like I said over here, we primarily focus on APM. This is kind of the stack that we see. So the top of the stack is this no instrumentation baseline visibility with code level context. And then we have all the user interfaces and API calls, and then the actual environment. One of the cool things about Pixie is that the actual monitoring data plane runs entirely within your cluster. So none of the data has to leave unless you're actually specifically requesting it in the UI, in which case it's still encrypted. So there's no data getting trucked over to the cloud. With things like the New Relic integration, you could actually get certain pieces of information sent over to the cloud if you're interested in doing things like alerting. The last thing I wanted to add before jumping into use cases and demos is that at New Relic, as I said, I was the GM of both Pixie and open source. We are betting big on open source. Pixie is now a CNCF sandbox project. So it is a community-managed open source project that you can check out. The website is px.dev if you're interested, and you can go see all the GitHub code over there as well. With that, the first thing I wanted to do is actually get Robbie Belson from Verizon to talk a little bit about how they're using Pixie to monitor Kubernetes at the network edge. So let's see if this video plays.
Hello everyone, and thanks for tuning in to learn a little bit more about 5G Edge. My name is Robbie Belson, and I lead our developer relations efforts here at Verizon. And today I wanted to tell you a little bit more about mobile edge computing, and particularly how you can use Pixie to help with all of your observability at the network edge. But before we get there, let's start out about why mobile edge computing. Especially in light of the pandemic and beyond, customers are desiring increasingly immersive, contactless mobile experiences. And we see this inextricable link between latency and conversion and ecosystem stickiness. And so as you think about some of these challenges in terms of delivering these increasingly mobile and immersive experiences, in the face of ever-increasing consumer demands, the question that we found ourselves asking here at Verizon is around the question of, can the network finally become an asset to application performance? And if so, would we be able to create a platform whereby developers wouldn't have to learn a new framework or no new tool, rather? They could just use the AWS cloud that they know and love. And thus, Verizon 5G Edge with AWS Wavelength was born. The idea is fairly simple. If you think about a 4G or 5G network, you have all of these radios for a given geography that converge to a single convergence point. And that point of convergence is precisely where the packet core sits, where all of this mobile traffic finally becomes an IP address. And precisely there is where this compute lies. So it's at the edge of the carrier network, and the beauty of that is, from a latency perspective, you don't have to egress the mobile network to the broader internet, which, as we know, was designed as a best effort service. So you can cut out a lot of that non-determinism associated with the latency from the internet itself, and keep your compute and latency-sensitive applications within the mobile network itself. And 5G Edge with AWS Wavelength is available today, at the time of this recording, in 13 different cities all across the US. So with that in mind, as you think about application architectures, what are customers actually building today? At the highest level, take a look at what you're seeing on the right-hand side. You have a VPC, and that VPC consists of a series of availability zones, or subnets. And today, you can create an arbitrary series of subnets within the context of the CIDR range afforded by your VPC. But today, we've introduced the concept of a wavelength zone that behaves much like an availability zone. You see it as just another subnet within your VPC section of the console. But it just so happens that that wavelength zone is actually within the Verizon carrier network. And you can have a number of wavelength zones behaving as subnets within your VPC. And then from a connectivity perspective, you have something called a carrier gateway. Very similar to an internet gateway, but that NAT capability it's providing is from private IPs to Verizon carrier IPs, or a pool of IP addresses that are allocated within the context of that network border group for Verizon. What this means is it's a lot of the similar functionality you know and love on AWS. You're still using a VPC, you're still taking care of subnetting. The route tables are very similar, that default route going through the carrier gateway instead of the internet gateway. Fairly similar stuff, and worth noting that that wavelength zone can seamlessly connect back to any of the other availability zones that house your subnets within that VPC via the service link, or highly available fiber by way of all of these different private IPs connecting to one another. So this is incredibly special, but worth noting that in a Kubernetes environment, things get a little bit more challenging. The reference architecture that AWS has proposed for EKS is as follows. You have a control plane in region, so you'd launch an EKS cluster just as you would any other way. You choose at least 2 subnets within the parent region, so US East 1A and 1B as an example. And then for your nodes, or node groups as EKS refers to it, those node groups can be launched in wavelength zones, multiple wavelength zones if you so choose, but they're self-managed worker nodes. There's no such thing as Fargate or manage nodes at the edge. And thus, if you go to the EKS console and you look at nodes, you won't see them. What you end up doing is you use a CloudFormation template that AWS has for these self-managed worker nodes, saving you a lot of time And then as long as your security groups and the cluster endpoint for EKS is set appropriately, then they self-register to the control plane accordingly. Easiest way to do so, public endpoint on EKS and a carrier IP attached to each of your nodes, and you're good to go. But that only takes care of the connectivity from nodes to control plane. What about the observability? Said differently, if I have pods somewhere in an availability zone, and I have pods in a wavelength zone, what is the latency between those pods? And this is so much more complicated than before, because the latency between two pods in one availability zone and a second availability zone will be much different than a pod sitting in an availability zone and a wavelength zone, or two different wavelength zones. As one such example, if you have a pod in the Boston wavelength zone trying to communicate to a pod in the New York City wavelength zone, that traffic is likely, if not going through the carrier network, if it's going through the private IP addresses, the pod IPs, it's actually going to go through the USD-SWAN Northern Virginia region. So the traffic patterns here are a little bit non-intuitive, you might say. And something or someone has to be measuring this. And all the examples I've just discussed are in the context of east-west traffic, within your logical data center, rather. But worth noting that north-south traffic is also a problem, because how can performance monitoring play a role in traffic from the mobile device, or IoT device, to one or many of these different wavelength zones? And the wavelength zone closest to you may change over time. So with these questions in mind, we teamed up with the Pixie team to think about what this might look like. And so step one, we knew, was out-of-the-box instrumentation, fully automated. And what I love about Pixie is that auto-telemetry capability, and from a local compute, the fact that the metrics are kept within the cluster. It's so incredibly powerful for these edge computing use cases. And so what we did is we built a Terraform module where basically all you need to provide is your Pixie deploy key and your Pixie API key, your EKS cluster name, and you're good to go. Everything just builds. The EKS cluster, you can select which wavelength zones you want your node groups to live, and off you go with auto instrumentation as you see here on the right-hand side. And we believe that this is only the start. As you think about east-west traffic monitoring, you can use pixel scripts to do all sorts of clever network flow monitoring. The simplest way you can do that today is if you have a sense of the CIDR ranges for each of the subnets in your wavelength zones, as you get these network flow graphs, you can use pandas within these pixel scripts to say, aha, I can get the pod IP or the node name, and the node name roughly corresponds to the subnet, so I can then figure out, the 10.0.3.0/24 subnet must be those of the Boston wavelength zone. You can start to get really clever in terms of how you slice and dice your east-west traffic from an observability perspective using the flexibility afforded by these pixel scripts. But beyond east-west traffic, we started to think about the north-south traffic problem. And first I want to introduce an API that Verizon developed and then position how, beyond just Pixie, you can use New Relic to do a series of really clever performance monitoring optimizations. So simply put, Verizon wanted to solve the problem of, if I'm a device, what is the closest wavelength zone to me at any given point? And we developed this API called the Edge Discovery Service, which essentially is a service registry that you as the developer populate your endpoints, IPv4s, FQDNs, doesn't matter. And then when you're looking to find that optimal node, you simply query the service registry, providing your IP address as that mobile device, and it will tell you, aha, the closest wavelength zone to you is the New York City wavelength zone, and here's your IPv4, and then you go ahead and connect accordingly. So with this API, the question that we had was, maybe you can think about monitoring in this context, and here's a great example of what you might do. Let's say in a crowd analytics use case, you have these LiDAR cameras constantly sending video, and you need to make sure that the latency from that LiDAR camera to that initial ingress is X milliseconds. So what you could do is you could create a new Relic alert that says, above a certain latency threshold, if triggered N number of times, trigger an alert. Today, you could send via webhook to Slack or wherever, but that wouldn't change really anything about the connection from that mobile endpoint to the mobile device itself. But now with the Edge Discovery Service, what you could start to think about are the following patterns. That as a result of triggering that alert, a webhook could send a message to the Edge Discovery Service saying, hey, LiDAR camera, perhaps you want to reevaluate what the closest wavelength endpoint is to you, and reconnect accordingly. And this is how we start to think about network intelligence in the context of Verizon 5G Edge, because it's no longer just about application metrics, CPU, memory utilization, etc. It's about how network intelligence can deliver unprecedented workload orchestration capabilities. And with that, I invite you to continue the discussion with us here at Verizon. You can check out our blog on Medium, our developer newsletter, our GitHub 5G Edge tutorials, and so much more. Thanks for having us, and enjoy the rest of your event.
Awesome. So that was great to hear from Robbie. He's actually going to be at the New Relic booth at 5 p.m. if you want to hear more details about how the Verizon 5G Edge and New Relic's Kubernetes monitoring works. We'll also be there to answer any questions about New Relic's Kubernetes monitoring along with Pixie. And with that, I'd like to get Natalie to come and do a demo of Pixie and the integration.
All right, thanks, Zane. Cool, so I'm just gonna show a demo of how you can use the New Relic Pixie integration to troubleshoot a different kind of, I guess, issue than, Robbie might be using Pixie for, which would just be troubleshooting web applications like a lot of us, need to maintain and make sure stay running. So basically, just for context before I show the demo, I have a Kubernetes cluster, and it has deployed Pixie. And as Zane said, basically the way this works is that we have an eBPF-based collector on all of the nodes in my cluster, and that will work in order to automatically collect HTTP data, DNS data, metrics like network statistics and infrastructure metrics, and even flame graphs for application profiles. Let me just switch this. All right, it worked. The demo gods are with me. Okay, cool. So as Zane mentioned, Pixie is a completely open source project, and so you can just get started with it today by going to our GitHub and seeing the source code. And it's a CNCF project, so it's part of the same foundation that has Kubernetes, Prometheus, and other cool applications. New Relic has a really great integration for Pixie, so it's a great way to take this data that Pixie is collecting in your Kubernetes cluster and use it as part of your New Relic experience. And I think, like Zane was saying, it can be really hard to get started with all of this information, collecting all the telemetry data that we need in order to debug our applications. And one cool thing about this integration is in one single Helm command, you can get really good baseline visibility into your Kubernetes cluster. And so I'm going to show you some of the views that you get if you were to run that Helm command. So in my Kubernetes cluster, I can see that we've already detected that there are various services running. And I can see information about that. And it has detected Kubernetes deployments and various Kubernetes pods. So I have multiple demo applications running on this cluster, actually. So let's check out a pod for one of my services, the catalog service. After just running one Helm command, I can see things like the CPU usage, the memory usage, and things like throughput of my requests over time. One of my favorite features is sometimes you want to know, why are things slow in this one pod? Like, why is the request taking too long? What is the bottleneck in my application? And so one cool feature that we provide is the ability to basically see flame graphs for your application and figure out what are the parts of it that are taking a really long time, what are the parts of it that are consuming the most CPU. And you can see down to the exact function that is being called where that energy is being spent. We can also automatically connect these pods to the services that they're a part of. So let's investigate more about this catalog service. It's grouped under this Open Telemetry Services view. And I just wanted to take a quick moment to talk about Open Telemetry because I think it's something that at New Relic we're really passionate about. Open Telemetry is another open source initiative that basically provides an open source specification for telemetry data. And this sounds, maybe like a niche thing, but it actually has really big implications, because when all of your telemetry data is in this common format, it's all interoperable with each other regardless of what was the collector that collected it or what tool are you using to analyze it. So that's one thing that I wanted to highlight. So Pixie is plotting the response time for my HTTP requests for the catalog service, my throughput, my error rate. Very nice, 0 error rates, that's performing well. And another cool thing that it can do is it can actually tell me which of my endpoints are slow, which of my endpoints are being hit the most often. And a lot of times in our endpoints, we have like wildcards in the URL parameter, and we automatically collapse these into logical endpoints to make it easier to debug what's going on. Because I think a lot of us have seen that just because your service has a really low latency doesn't mean every single endpoint is behaving well. We can also see the database connections that this service has. So we can see the queries that are being run and if any of them are taking too much time. So I'm going to switch over to another view here, which basically is another way of looking at the Pixie data in my cluster. And it's called the live debugger. And this is really powerful because it can give you both high-level views of what's going on and also allow you to dig down into individual requests and fine-grained information. So kind of like the landing page is this cluster-wide view. So here I can see the connections between all of my services, which services are talking to which. Maybe they're talking to some external IPs, and then giving some highlighting for the fact that this connection may be slow or full of errors. I can see things like, what are the nodes in my cluster? What are the namespaces that are present? What are some high-level statistics about those and the services that are present? If we were to click into a specific namespace, we can see information about that namespace in a more filtered view. I said before that we had infrastructure statistics as well. So looking at the nodes in my cluster can be a really good way to just see, is something spiking? Do I have too many pods scheduled on a particular node? Is one node sending a lot of unexpected traffic out? And I kind of keep emphasizing this, but all of this is just provided for you out of the box as soon as you deploy with one single Helm command. And that is the power of eBPF telemetry data collection. So if we were to click into one of these nodes, we can see our friend the flame graph again. And we want to group this by pod. And basically see, like, for the pods on my node, which of them is consuming the most CPU? Which of them is writing the most traffic to disk or sending it over the network? We can also see which of these is consuming the most CPU on the node, and each of these basically corresponds to a different pod running on my node. I think the common joke we have is that it's always DNS when there's a problem in your system. So you might also want to look at something like, what's the flow of the DNS requests in my cluster? We can see that everyone seems to be hitting kube DNS as expected, but we have personally found some DNS misconfiguration problems using these views. And then additionally, sorry, I got a little stuck in a scroll bar there. Personally, I really like seeing the raw data. Like sometimes summaries are really great, but a lot of times when you're looking at a particular application bug, you need to see this specific request failed and here's why. So in this view, I can actually look at every single raw HTTP request that we've collected in the cluster. What's the body, what's the response? I can filter it to say, okay, I only want ones that have a 500 status quo code because maybe a user reported a 500 error. All of these things are scriptable, and so if there are views that you would like to see, you can contribute them to the GitHub community as well. And we would love to have people check out the project. Just Pixie.io/Pixie, and yeah, I think that we're really excited about the integration that we have with New Relic. We think it's really powerful, and we hope to help developers everywhere debugging their Kubernetes clusters. So With that, I will transition back over to Omid, who will give more information about this really powerful eBPF-based telemetry data collector.
Great. Thanks, Natalie, for an awesome demo and showing everything that Pixie can do. So as Natalie said, what I wanted to take some time to talk to all of you about is how the magic happens, right? So we wanted to take a little bit of a look under the hood and see how we provide this auto-telemetry, as we call it, right? How are we providing you visibility into the workings of your applications on Kubernetes without requiring you to ever change a single line of code or even redeploy your programs? And how are we giving you all the data that Natalie just showed, right? I should have clicked on that. So under the hood, what's that? Oh, sorry. Oh, yes, sorry. Thanks, Aaron. Sorry, should have switched back away from the demo. So I'm going to be talking about those. So talking about the data collector, and that's the piece that's doing all the magic under the hood, and uses this technology called eBPF that's been referenced a number of times. So under the hood, Pixie and the eBPF technologies that we use is really, we organize it into a number of different data sources, right? So we have, for example, a data source that we plug in that goes and gets all the process stats. So all the CPU stats that you saw that Natalie was showing about how much CPU utilization there is on the node comes from that. We have stuff for network stats. We have a data source for protocol tracing. We have a data source that's driving the application CPU profiles. And then we have other kind of more advanced BPF features, one called BPF Trace, which has an integration with a community project, which is called BPF Trace. And another feature that's alpha right now that we'll advertise more later, but that does dynamic logging. And so we have this extensible architecture where we can plug in these different eBPF sources to collect the data and then feed it into the Pixie framework, and then, again, drives all of the cool stuff that Natalie showed. So for process stats, let's start easy, right? So for process stats, this is something you'll see in most observability tools, right? You want to see for your pod how much CPU it's using, how much memory it's using, how much I/O it's using. For this, actually, Linux does a pretty good job of exporting this data. So we can just go straight to Linux and grab the data, and you don't even really need to use eBPF, although you can to make it even more efficient. But you can kind of get that table stakes data out pretty easily. So we obviously provide that sort of information. But in addition to that, we have the flame graphs that Natalie showed, right? And so this is a feature, again, you didn't have to change anything in your code. There are a lot of pretty cool and awesome profilers in different languages. Like if you have a Go application, Go has its own profiler, and you could use those things, but you often have to jump through a few hoops to get that stuff enabled. Here, using eBPF, without any code changes, we're able to automatically collect all this information and then show you a flame graph, which is a cool visualization that shows you where your code is spending its time. And with a flame graph, you're generally looking for the kind of the x-axis. The bottom is like 100% of your application's time. And so you're looking for bars or functions that are fairly wide, because that's telling you that a lot of time was spent in that particular function, right? And so you get the entire, you not only get the function that you're in, but you get the entire call stack. So you know who called that function as well, and how you got to that function, and why it's spending time there. So it's a great tool as an application developer to figure out, if something's using too much CPU or something's being slow. We often jump to this view and kind of take a look at it and see if anything looks weird or abnormal, or if something's using way too much CPU, like we want to optimize it. We've actually even used this feature to optimize Pixie itself. So we kind of use it to look at where Pixie itself is spending its time to optimize it. Right? And so all this is driven by eBPF. Under the hood, eBPF, and I'm going to get into a little bit more detail about how eBPF works, but it's essentially periodically kind of waking up, you can think of it like it wakes up, takes a sample of where the code is, and immediately returns the execution back to the program. So it's very low overhead. It's less than 0.1% overhead, the eBPF probe that's kind of collecting all these stack traces. And then we take that information and turn it into a nice, pretty visualization. The other major thing that you saw in Natalie's demo was the protocol tracing. And that was essentially the feature where we're able to capture every, so one pod is talking to another pod, it's sending an HTTP message. We get to trace that using eBPF again, right? We capture it, we essentially snoop that message, we collect it, we put it in tables so that you can query, you can search for HTTP response codes that look like errors, or you can search the body, some particular tag within the message. You can do whatever you want. But under the hood, it's eBPF that's snooping all this data and populating the table so that you can kind of see what's going on in your cluster and in your application. And it's also this data that's driving those service maps and the flow graphs that were present in Natalie's demo, right? So we take all this information, and then we see who was talking to who, how many messages were sent, what's the throughput, all that stuff is all driven from this eBPF protocol tracing. And Natalie already showed it, but you saw the raw data, right? You can see individual HTTP messages. You can see that there was a GET. For example, here you see that there was a GET to a carts endpoint, and there was a POST to a payment auth. And you can even see the body. We get like full visibility with eBPF. So we have these different components that we plug into Pixie at the data collector level, and it's driving everything that's the experience that you see. And again, I'm just going to stress this one more time. It's all without user instrumentation or redeployments. And I stress it because that's really, when we put this project together, it's really what we wanted to do. We wanted to make things easy for application developers. When you're troubleshooting, the last thing you want is to have to go and like re-instrument something or jump through some hoops to figure out how to get that extra data. You just want to be able to jump to something and say, oh, OK, I see what's going on in the application. I've got a clue now. I can figure out what went wrong, right? In that moment when things are going wrong, it's the worst time. You don't want to be going and adding instrumentation or trying to modify your application. And again, it's all powered by eBPF. OK, so we talked about how eBPF drives a lot of Pixie. Now, what is eBPF, right? In the observability world, eBPF is really taking off. It's really a powerful tool. And the one analogy I like to give of eBPF, first of all, I should say that eBPF is a very broad field, and it can be used for various different things. It can be used for observability. It can be used for security. It can be used for networking. And so I'm talking more about it in the context of observability today. And in that context, the analogy that I like to use is that it's like an automated debugger. So if anyone's ever used a debugger, you set a breakpoint on a certain function, and you say, when I reach this function, like stop the execution of the program because I want to poke around and see what's going on. Like I want to see the value of a particular argument or a variable at that point when I set the breakpoint, right? An eBPF probe, as it's called, is very similar. You specify a location in the code where you say, I want to put a trace point. So instead of a breakpoint, it's a trace point. But it's analogous. And so when you set that trace point, what's going to happen is when you reach that instruction in the code, or when you reach that line of code, it essentially interrupts the execution of the program. But unlike a breakpoint in a debugger where it stops it and there's user intervention, it essentially runs a BPF program. So it's kind of like a script. You say, OK, now that you've reached this point in the code, go and read the argument and store it in a certain location, like push it out, and then immediately resume the execution of the program. And so this is what eBPF in the Linux kernel lets you do. So the example I have on the slide here is we put an eBPF probe on this function. We say anytime send pong is called, right, we want to trace that. And then on the right-hand side, you say what to do when you reach this send pong function. So you say when send pong is hit, then run this eBPF program, and we're just going to increment a counter. So that's the most like kind of basic thing you can do is just count, for example, the number of times you hit a line of code. But you can do a lot more. Like we do for our stuff, we're going to actually go and capture the data when a message is sent, for example, so that we see all the HTTP traffic in your entire application. The initial reaction I often get when I explain eBPF to people is like, oh, wow, that's powerful. Like, you can do a lot. That also seems really unsafe. Like, you can go in and stop the execution of my program. What if you mess something up? What if the eBPF program goes into an infinite loop and it never comes back? What if it corrupts memory? All these sort of questions come up, right? So can you do whatever whatever you want with an eBPF program? Not quite. So this is the good news. The Linux developers who put in eBPF put in a guardian there. It's called the eBPF verifier. And so before you can run an eBPF program, the verifier actually takes a look at your program and analyzes it and kind of deems whether it's safe or not. It kind of checks for things like, does it complete? Does it ever go in? Does it look like it might even possibly go into an infinite loop? If it might even possibly go into an infinite loop, it says, nope, you're not allowed to deploy that. Or is it accessing memory that it shouldn't? Or is it have too many instructions, so it's going to take up too much time? All these things are conditions that the verifier checks. And it's great for the users, or like the users of observability tools, because you have some confidence that there's this guardian in the way that's protecting the stuff that we at Pixie do, right? When we deploy our eBPF probes, we're not going to mess up your applications. It's a thorn in our side because if you, as an eBPF developer, if you ever have to work with it, you're like, why? Why is it rejecting this code? It looks perfectly safe, right? It's very actually hard to work with because it's so conservative with what you can do. So that's the great news about eBPF. There's also an analogy to kernel modules. Like another way to do things in the kernel to get observability is through kernel modules. But eBPF arguably gives you a much safer way to collect data than through a kernel module, because again, kernel modules are not guaranteed to be safe. They can actually crash the kernel, but eBPF can't. So I wanted to give an example of how eBPF drives the APM data that we have, and this is just one example that I'm going to provide. Right? I talked about the profiler earlier. That was also driven by eBPF, but I'm going to talk specifically about that protocol tracing feature. So protocol tracing, again, is that feature that snoops all the HTTP messages or other protocols that you have, like Postgres data, MySQL. We have a bunch of different protocols that we support. So how does that work? So let's get a little bit more concrete with that, with an example. So you have your Kubernetes application, and it's running in a pod. Let's say you have a pod, right? And every time a pod wants to send a message to another pod, let's say it uses an HTTP library. That you say send an HTTP message. Eventually, that message comes down, and it needs to go over the network. So it comes down to the kernel, and a kernel system call is made. There's kernel system calls like send to send a packet, receive to receive some data. There's a connect call to actually make the initial connection. So if we were to go and put a trace point, or we do put trace points on these syscalls, we say every time that the connect call is made in the kernel, we put an eBPF probe on there, and we say, stop the execution of the program just very, very briefly, go collect information about who you were connecting to, who's on the other side of the connection, and then immediately resume the execution of the program. And so we collect this information with eBPF. Similarly with send, every time there's some data is sent over, like the body of the HTTP message or the HTTP message itself, or Postgres or MySQL or DNS, for example, we're going to stop the execution of the program very briefly, collect the data, and immediately resume it. And that's what the eBPF probe does. Right. Same thing with receive. And so you kind of start getting an idea of how we're collecting this data. The probe gets the data, and then the probe, eBPF has a way of exporting data out to user space. So we capture the data, and then we export it out to the Pixie Edge module, which is our user space program. And then from there, we kind of take over and parse the data and kind of eventually get it up into the nice form that you see in the UI. even cooler, at least in my opinion, is that you can use this approach to trace traffic that's encrypted. Right? So you can put a breakpoint, or a trace point rather, essentially anywhere in your code. So you can put a trace point on, for example, your TLS library to say every time that you send some data that's meant to go through your TLS library, like OpenSSL, for example, to get encrypted and sent out over the network, you kind of say, at the interface of it, at its input, before it gets encrypted, like snoop the data. Right? Put an eBPF probe right there to capture the data and kind of push it out to Pixie so that we collect all the communications. And so we can also trace TLS or SSL traffic out of the box. Again, I'm going to sound like a broken record, but no instrumentation required. And you don't even need to redeploy your program. It just kind of just works out of the box. So, and the credit goes to eBPF on this stuff. It's just so awesome, like it can do these sort of things. And then so kind of putting the rest of the picture together, like we get the data from eBPF. In the Pixie Edge module, we're taking all this data and keeping it located together by connection in these objects we call connection trackers. And then we know what protocol, or we detect what protocol the data is, and then we parse the protocols and put it into a structured form, like that HTTP data that you saw earlier in Natalie's demo. Like you'll get a field that says what was the HTTP method, what were the headers, what was the body, what was the response code. We put it in a structured form, stored in tables, and then from there you can query it and get it into all of the nice visualizations. And we support a bunch of protocols today, and you can see the list on the slide. So it includes even things like Kafka, Redis, and the list is growing. So it's an open source project. If anyone wants to contribute a protocol, it's open. You can add protocols into Pixie as well. And so then the result of that, right? I mean, you don't really need to know anything about eBPF to use this, right? So I'm giving you a view under the hood of how it actually works. And eBPF is pretty cool technology, so I think you're going to be hearing more and more about it. But really, at the end of the day, you really don't need to know much about eBPF if you don't want to. It's just what powers Pixie and what drives the ability to get these service maps, for example, and information about who's talking to who, and the amount of network traffic, high throughput connections, things like that. All of it's kind of driven automatically by eBPF. With that, I'm going to call Zane back up onto the stage to wrap things up.
Thanks so much. So I think just a couple of things to wrap things up, and we'll take questions as well. So I think Natalie mentioned this a few times, but we really like OpenTelemetry at New Relic and also the Pixie project. All the integration you saw between Pixie and New Relic actually happens through OpenTelemetry, so it's all based on open standards. And it also allows you to use a whole bunch of other tools that you might be already using or want to use, things like Grafana or Prometheus. The next thing I wanted to mention is that New Relic has a developer appreciation party tomorrow, so please stop by between 8 to 11, and the RSVP link's there. And with that, thanks a lot. And check out our GitHub repo, community Slack, and sign up for an account. And if there are any questions, we'll take them now.